Good evening to every Australian participant and good morning to Martin and other Europeans. And I know there are also some people from Asia, so good afternoon as well. Now, I don't need to introduce Martin Heirer. Everyone knows about his Fields Medal and about the theory of regularity structures, at least everyone heard about this theory. But let me only add a few words about other Martin activities that go far beyond only regularity structures. He has a lot of contributions to all areas of stochastic differential equations, ordinary and partial differential equations, especially to ergodic theory, to stochastic fluid dynamics, to multiscale systems, to homogenization, and I could still continue, but I will stop now. And please, Martin, tell us about Taming Infinities.
Okay, thank you very much, Ben. Thanks a lot for the introduction. It's a pleasure to be virtually in Sydney. Yeah, so what I'm going to talk, so this is sort of colloquium style talk, right? So it's going to be essentially without technicalities. The sort of infinities that I want to talk about today, so they're the kind of infinities, they show up originally, they showed up in the development of quantum field theory. So in the very early days, people tried, so in the early days of quantum mechanics, so that was sort of the late 20s, people tried to build a theory of quantum electrodynamics. And well, so they did what you're supposed to do in physics, which is make an educated guess of what the form of your theory should be, right? And then the form of your theory, what I mean by this is you write down maybe a Lagrangian or Hamiltonian or whatever, but typically that function depends on a number of constants, and they would be, you can interpret them if you want as the fundamental constants of nature, maybe like mass of the electron, charge of the electron, things like that. And so what you do is you write actually a family of theories that depends on all of these parameters. And then you start to do experiments, you make predictions of the theory, the predictions depend on these parameters. You make experiments, once you've made enough experiments, you can kind of fit the parameters, and then you can make new predictions, right? So a theory isn't really useful unless you can really make new predictions. So one corollary for that, so sort of the important takeaway for us from this is that a theory is only a physical theory if it depends on finitely many parameters, right? Because if it depends on infinitely many parameters, you can actually never determine what the theory is. And that means that you can essentially never really make new predictions. So of course, it comes with caveats. It could be sort of infinitely many, but it really depends very weakly on many of them. But then effectively, it really means finitely many again, right? Okay, and so in this particular case, so sort of the theory that people came up with, in some sense, it wasn't quite complete in the sense that the output of the theory is actually a sort of a formal power series. Okay, so you have this constant here, which is a constant of nature. It's a special kind of constant of nature in the sense that it doesn't have units. Okay, so it's one of the few constants of natures that actually comes without units. So it's an actual number. Okay, and it's a small-ish kind of number. Okay, so it's not just small in the sense that the Planck constant is small, because the Planck constant is small, but it's just small in our unit system, right? You can just change units and you can put yourself in units where the Planck constant is 1. Here, this one really doesn't have units. So it's, in every unit system, it's 1 over 137. It's not exactly 1 over 137, but plus minus less than 1%. And so outcomes come in formal power series in that constant. And it comes with, if you want, like a cooking recipe to compute the coefficients of that power series. And what people did at the beginning is to just compute the first coefficient. So and then you have a kind of approximate theory. And I think Oppenheimer, or maybe one of his students, were the first to try to actually go to the higher order for a specific experiment. And what they realized is that when they wanted to do the calculation to next order, you actually end up with infinity as the coefficient, right? So the problem here, you have a power series. So you might ask yourself, when does that power series converge and things like that. So here it's not a question about the power series not converging. It's about the second term of the power series being infinite, right? So there's no question of convergence after that, right? And so, but remember I told you that, well, what the theory really does is it gives you kind of a cooking recipe. So it tells you, here is this complicated integral that you build, and then you actually have to, you build a complicated function, you have to integrate that function, you combine these things and so on, right? So you have sort of various steps like that. And the way it goes wrong is that at some point, if you want, the cooking recipe asks you to integrate a function which is not integrable. Okay, and then of course you just end up with infinity. And so at the time, people actually, well, of course, first reaction could be to get depressed and to say, well, that just means that the theory was rubbish and I have to restart from scratch. Second reaction, if you are, one of these people, most of whom got a Nobel Prize for that, then you don't get depressed. You just say, well, okay, so can I kind of understand that, or can I fix it in some way? And they came up with a fix at the time, which sort of seemed very ad hoc, which was essentially to say, well, there are these diverging bits that show up because you're supposed to integrate a function which is not integrable. So let's just pretend that the integral is finite and take it as a parameter in the theory. Right? So essentially what you say is, well, you have that non-integrable function, integral is infinity, but let's just pretend it's finite. And then of course you have exactly the problem that I mentioned at the beginning, right? So if you just do that and say, well, okay, so now that's a constant that I don't know what it is, I have to determine it. Well, then whenever you have one of these, diverging integrals, you get a new constant, and then you just end up with infinitely many constants. And again, your theory is sort of useless because it doesn't actually have any predictive power. The trick there is to realize that many of these functions, even though if you want, they are not all the same functions, but they kind of diverge in the same way. So if you want, the number of ways in which the functions diverge is essentially finite. Right, so the way you can think of it is, you have a function which is sort of like 1 over absolute value of x, it kind of diverges, but then you have another function which is not exactly 1 over absolute value of x, but near 0 it's very close to 1 over absolute value of x, and it sort of differs from it by something integrable, right? And then if you give the first function the integral of the first function some value, well, then the second one, you better give it the value which is the one you gave to the first one plus the integral of the difference, right? So you want some kind of consistency of your value assignments, and if the ways in which things diverge is sufficiently rigid, so if there's sufficiently few ways of diverging, then it may well be that you can do that by only having to introduce finitely many new values. Okay, and that's kind of what happened. Now that worked extremely well, but of course it's still, it sounds like a cheat, right? I mean, in some sense, you start off from something, it gives you some kind of cooking recipe, then you modify it in a totally ad hoc way, it gives you kind of a different theory, and then that one somehow magically gives you answers that actually fit the experiment pretty well. Of course, you could say, so as a physicist, you say, well, everything's fair game. I mean, a physical theory, nobody, all it has to do, it has to be a cooking recipe that allows you to make predictions, right? At the end of the day, if the predictions are fine, then the theory is fine, right? But still, I mean, people were a bit queasy about it. So this is what Dirac had to say about that. So he said, this is not just not sensible mathematics. Sensible mathematics involves neglecting a quantity when it's small, not neglecting it just because it's infinitely big and you don't want it. And well, Feynman here said something a bit similar. He said the shell game that we play is technically called renormalisation, but no matter how clever the word, it's still what I would call a dippy process. But as already mentioned, it works extremely well. So in some sense, from a experimental physicist point of view or theoretical physicist point of view, there's nothing wrong with having a theory that was maybe derived in a slightly funny way. Now, let me try to give you some kind of cartoon. I think that sort of understanding that came later, sort of that was developed sort of over the years, of a way in which we can actually understand what's going on in a way which is maybe somewhat less ad hoc. Okay, so let me try to explain that. Okay, so again, physical theory, basically a physical theory, you can view it as a map that takes two types of arguments, right? So the first argument is the physical constants, that's like the parameters that you want to determine. The second type of argument is sort of the experimental setup, right? So it's which experiment you perform. And then depending on what are the values of the fundamental constant of nature and what experiment you perform, it spits out a number, or maybe some other type of mathematical object, but let's say you can pretty much encode anything in numbers. So it spits out a number. And well, now the problem that we have is we're not actually given a map in the sense of value assignment for every pair of values, but we're actually rather given a kind of cooking recipe. Okay, so we're given a number of steps that you have to perform in order to compute that map. And at some point, one of the steps goes wrong, right? So here it's the sort of integrating the non-integrable function. So now the idea is what you do is you somehow fix the theory. So in this particular case, the way in which things go wrong is actually, it goes wrong when you start probing the behavior of the theory at very small scales, right? And that's somehow the analog, if you want, of the 1 over x kind of diverging at x equals 0, and you think of x as being the scale, right? Some sort of a length scale. And so then what you say is, well, at very tiny scales, like way below the size of an atom, there's not much hope that we ever figure out what's going wrong on anyway, right? I mean, none of our experiments can go and see what happens there. So who knows? I mean, the theory could be something completely different down there, right? And so what you do is you just fix it in a basically arbitrary way at very small scales, right? So you just change the theory in such a way that, what happens at kind of larger scales doesn't change, but what happens at tiny scales, sort of, you just modify it in a sort of ad hoc way, in such a way that it spits out finite numbers. Now, of course, the problem is that it's going to spit out very large finite numbers, right? And sort of like, now you would want to send epsilon to 0, and of course, things are going to diverge as epsilon goes to 0, right? Because that was the problem you had in the first place. But now you also end up with a whole bunch of, well, okay, so you also end up with these sort of new parameters which describe, the way in which you fix the theory at small scales, right? So there are lots of different ways of fixing it. So you choose one in a sort of arbitrary way. You could have chosen another one, and that would be encoded here in these sort of unphysical parameters, because that's things that you would expect to never be able to actually determine by experiments, right? And so now you would want to send epsilon to 0. And of course, if you just send epsilon to 0, things blow up. But what you have here is, well, you always have a group acting on these parameters of your theory. So in a most general sense, well, you have just the grip of diffeomorphism, right? You can always somehow do a change of variables. So you can decide to parameterize your parameters in a different way. So you can do like changes of units, but it doesn't have to be linear changes of units. You could do nonlinear changes of units or something, right? So you can always somehow change the way in which you parameterize your family of theories. Okay, so that doesn't do anything in a way, right? So it just changes the numerical values that you assign to your parameters. But now what you do is you try to find a bunch of elements in that group of basically reparameterizations, so that now what you do is you take a limit in the following way. So you send epsilon to 0, but you simultaneously reparameterize your theory. Okay, so you kind of reparameterize your theory, so you apply these group elements to the parameters of the theory. So it doesn't change. So at every epsilon, you're looking at the same family of theories, whether you apply that thing or not. right? It makes no difference to the family of theories. It just, all it does is it changes the way you assign numerical values to a given theory, okay? It doesn't change the family itself. And now the hope is that you can do that in such a way that this limit actually exists, and furthermore is independent of the way you fix things at small scales. Okay? I mean, at least independent, say, in some class of, you know, regularizations. And so if you can do that, then you say that your theory is renormalizable. And you see, so if this actually happens, there's no reason a priori for this to happen, right? It's kind of a miracle when it does. I guess somehow the realization is that, well, actually, in many situations, this is what's going on. And this miracle, if you want, does actually happen. So the outcome that you end up with here is, so if you end up with basically a theory that has the same number of parameters as the theory that you started from, right? So your parameters, your space of parameters here hasn't actually changed, right? So lambda still takes values in that capital lambda. It's just in some sense their interpretation, also the interpretation of the numerical values that you assign to these things has changed. And well, so here, so this guy is Toft. So he was the first to show that the standard model, which is, you know, like the model which is supposed to describe all of nature except for gravity, is perturbatively renormalizable. So in some sense, so remember, so I told you that in a way the outcomes of these theories are these sort of formal power series. And so here it's renormalizable in the sense that you first fix an order of truncation of your power series, right? So you say, okay, I stop at order 10, for example, and then you perform the procedure that I just mentioned at order 10. So at every fixed order, you can perform that procedure. There's no proof that, you know, you can kind of exchange these limits or anything like that, right? So that you would want to somehow have the formal power series. You would want to actually do it on the full theory in such a way that the renormalized thing gives you a power series that converges. Okay, so that's not known. But order by order, you can renormalize these things. Okay, so now, so this was all pretty philosophical. Right? So it was, I tried to sort of remain at a very conceptual level. So let me try now to be sort of super concrete and give you an example, you know, where exactly this phenomenon happens. Okay, so the example is the following a family of distributions. So now distributions in the sense of Schwarz distributions on the real line. And so remember, distribution is just a, you know, linear functional on the space of test functions. So it takes as an input a function, it outputs a number, and it's, well, linear in the test function, okay, and some continuity property. And of course, you know, the example that you've all seen is the Dirac distribution, which you give it a function, it spits out the value of the function at the origin or anywhere else. And also, if you have another function, if you fix yourself some function, say eta hat, that determines canonically, if you want, a distribution by saying that, well, the distribution eta acting on test function phi is just the integral of eta hat against phi. Okay, and so this works as long as eta hat is locally integrable. Right, so because the test functions of decay, say they're compactly supported, so there's no problem at infinity, but locally, you know, you need that integral to make sense. One remark is that basically every distribution is morally of that form. Of course, the Dirac distribution is not, but it can be approximated by things like that. And so you can always replace the delta. You've all seen in your analysis courses, you know, delta sequences that are functions that integrate to 1 and get supported on a smaller and smaller set. And if you take a sequence of functions like that and you integrate it against phi, then that converges to phi of 0. Okay, so that converges to a Dirac distribution. And so now the question is, can we define the following 2-parameter family of distributions, which would be sort of a over absolute value of x minus constant times Dirac. And now you see separately these two terms. Well, the second term makes sense, right? So because the Dirac makes sense, I can multiply it by any constants, no problem. But that one doesn't really make sense on its own, right? Because as we've seen here, if you want to interpret a function as a distribution, it has to be locally integrable, and 1 over absolute value of x is not locally integrable. So if I test this against the test function that, right, so if I take a test function that sort of looks like this, which is non-zero at 0, and I integrate it against 1 over absolute value of x, then, well, near the origin, the product of the two here is going to look like 1 over absolute value of x, and the integral diverges. So I don't know a priori what this means somehow, right? So if I just fix a and c, there's no good meaning to this expression. It's kind of ill-defined. So in that sense, it's sort of infinite, right? Because this bit is finite if I test against phi, and this is, well, essentially a times the integral of 1 over absolute value of x times phi of 0, which is infinite. And so now let's just follow our procedure, right? So the procedure is we want to somehow fix the problem in a somewhat natural way by modifying our distribution only locally where things go bad, right? And so here it's clear what goes bad. What goes bad is that 1 over absolute value of x diverges too fast. And so let's just cut it off in some way, right? So we just introduce some parameter epsilon. And for example, one thing I could do is I could just replace absolute value of x by absolute value of x plus epsilon, okay, in that formula. But I could, I could have done this in any other way. I could have replaced it by square root of x squared plus epsilon squared, for example, if I still want epsilon to have the same unit, or whatever, pretty much any other way of somehow truncating things near 0 without changing it too much, kind of away from 0. And so now I can rewrite, right? So now I replace my eta, it becomes an eta epsilon, and my eta epsilon would just be the same thing, but with a plus epsilon here. And now what I do is I do a smart way of reparametrizing these two constants, right? So this depends on these two constants, a and c. And now I want to do a change of parametrization of these constants that depends on epsilon, which is done in a smart way. I claim that this does the trick. So I look at the following collection of distributions. So I take a sort of nice cutoff function. So this guy, this chi, you should think of it as just being a function like that, right? It's compactly supported. It is sort of 1 around the origin. And I look at the distribution, which is, this distribution here. Now, if you look at this, you find that this distribution is exactly of this type, because what does it do, right? So here, the first term is actually just this term here where I've replaced x by x plus epsilon. The last term here is just this term here, except that the c, I call it c tilde here. And then there's this extra term here. But what's this extra term? This extra term at the end of the day, it's just some big constant times phi of 0, right? So actually it's exactly of the same form as this term here. It's just written in a funny way. Right? So I just choose a constant which happens to be, a times the integral of chi divided by x plus epsilon. So that's going to be a constant that diverges like log epsilon, if epsilon goes to 0. I just multiply this by phi 0, but what I do is instead of in the way I write things, instead of putting this term sort of together with this delta function term, I sort of incorporate it into this term here. And the reason is that, well, clearly, what you see is that here I have no problem sending epsilon to 0 now, right? Because the problem was that if phi is non-zero, then this integral diverges if phi of 0 is non-zero. But now here I just subtract, near the origin chi is 1, so I subtract phi of 0. So near 0, this is actually 0, right? So near x equals 0, this goes to 0 like linearly in X. And so this actually remains bounded. So it's perfectly integrable. Right? It's even much better than just integrable. So there's absolutely no problem for this to converge as epsilon goes to 0. Right? And so I take that limit. So I just, I just delete epsilon. So this expression makes perfect sense. And now I have a family of distribution which was obtained, by regularizing that guy. Just do a change of parametrization. All I've done is I've replaced C here by, I've written, if you want, C as C tilde minus or plus that integral here, okay, times A, which is sort of like a log epsilon. So I've only shifted the origin for C by about log epsilon. And by doing this, you see that this converges perfectly. And furthermore, it's clear that, what are the unphysical parameters here? So the unphysical parameters here is the way I fix things near 0 and the way I do that cutoff. But if I fix this in a different way, or I do the cutoff in a different way, you can actually convince yourself that you get exactly the same 2-parameter limits. The only difference that you see is that, the 2 limits are parametrized differently, right? Sort of like you get the same family of limits. It's just that the one that corresponds to A equal 1 and C tilde equal 1 for one limit might be A equal 1 and C tilde equal 2 for the other one. Okay? So it might be parametrized in a different way, but the 2 parametrization actually just differ by a finite shift in C. So as a family, it's exactly the same family that you get. Okay, and so that's the kind of feature that you see. Okay, so this is a very simple example, so you kind of see very explicitly what's going on. And now what I want to show is I want to show you sort of more, if you want, complicated or more interesting examples where exactly the similar, in some sense, exactly the same thing goes on, but it's more hidden. Okay, so it's less clear that something like that's going on. So the other example, the second example I want to give you is one where one may have the impression that it's really completely different. Okay? So let's start with just a random walk. So regular random walk, I choose some distribution for steps. So for example, moving to the right with probability 1/2 and to the left with probability 1/2, but it could be any kind of distribution on the reals as long as it's square integrable or something. And then what I do is I speed things up. So instead of doing a step of order 1 every time of order 1, I make a step of size about square root of epsilon every time step of size about epsilon. Okay, so I speed up the natural clock, so I perform steps every time epsilon, but I make very small steps. And it's sort of a standard theorem in probability theory, which, well, so that specific formulation was given by Donsker first, I think maybe in the 50s or 60s or something, but it really goes back to somehow proofs of the CLT. It's essentially a version of the central limit theorem. That shows that this actually has a limit as epsilon goes to 0 in the space of continuous functions, for example, if you sort of link your steps by straight lines. And that limiting random function is what we call a Brownian motion. Okay, so this is sort of what a Brownian motion looks like. So Brownian motion is now a random continuous function. So it's a probability measure on the space of continuous function. And if you draw a sample from that probability measure, it typically looks like this. Actually, I have let me see if that's going to work. So I have a sort of little animation here. I don't know if that sort of shows nicely through the internet, but what you should see here is one sample of a Brownian motion, and I'm kind of zooming out. Okay, and I'm zooming out more and more. What you see, it always looks the same, statistically at least. Right? So it always looks similar. So there's some self-similarity here. And these horizontal parabolas that you see on the screen, they are there to illustrate the fact that the way I'm zooming out is the way that keeps these parabolas fixed. Okay, so if I zoom out by a factor L horizontally, I actually zoom out by square root of L vertically. So I don't keep the aspect ratio. The Brownian motion is self-similar under that kind of scaling. So in some sense, what this tells you is that at every point, right, it's a random continuous function, but it's very irregular. You see that it looks very rough. And you can quantify how regular it is. Basically, at every point, it has a sort of square root of t type of behavior. Okay, so it's essentially, it's basically Hölder half. So it's actually not quite Hölder half, but it's Hölder for every exponent less than a half, and it's not quite Hölder half. Okay, so it essentially has sort of square root of t type singularities at every point. And so now what you can do is you can say, well, so this random walk you've seen from this picture, it sort of looks like the type of curves that you would see in, you know, the Wall Street Journal or something. If you look at stock prices, right, or if you look at whatever, Yahoo Finance, on normal days, okay, stock prices would roughly look like this. Of course, you know, if you look at the stock of a game shop last week, it doesn't look like this at all, because the kind of trading patterns you had do not at all fit, you know, the derivation, if you want, of, you know, random walk, because you lose the independence of the trades, and then you can kind of start to see weird behavior. But if you assume that sort of trades are independent and there are lots of small trades, you expect things to essentially look like a Brownian motion. And on normal days, for things that are traded in a normal way, that's more or less what you see. So you see something that looks like this. But of course, a better model for a stock price would take into account the fact that stock prices don't go negative, right? And the amount by which a stock price sort of fluctuates in a given day or in a given interval of time, you'd expect it to be actually roughly proportional to the value of the price itself, right? So if the stock price is $100, then it can easily fluctuate by a couple dollars in a day. But if the stock price is already just a couple dollars to start with, then it's pretty unlikely that it would just, you know, go to zero in one go. So a better model for stock prices, so, you know, that would be the next more naive model, if you want, for a stock price, where I multiply the step size with the current value of the stock as well. Okay, so now this I can rewrite it like this, right? So it means the increment of my stock price is square root of epsilon. No, it's the stock price itself times the square root of epsilon psi, but that was the increment of this random walk over the same interval, right? So if I compare the two models, I can rewrite my stock price model as, you know, increment of the stock price is value of the stock times the corresponding increment of a Brownian motion. And now that sort of looks like it looks like a numerical scheme for a differential equation, right? So it essentially looks like a time discretization of a differential equation. So if I'm an analyst and I want to kind of figure out some kind of nice limiting model, I would essentially formally send epsilon to 0 and say, well, I just pretend that these finite differences turn into derivatives. Okay, and so I get the model ds dt equal to s dw dt. And so I conclude that my model should be s of t is s0 times the exponential of w. Okay. If you do that, actually you get the wrong answer. Okay, so the claim is that this does converge as epsilon goes to 0, but it does not converge to s0 times exponential w. Okay. Actually, it converges almost to that. It converges to s0 times exponential w minus t over 2. So what's going on here? So first, could we have guessed that something should go wrong? Yes, because if you take expectations on both sides here, since I assumed that these steps are all independent, that means that that guy is actually independent of the current value. And so the expectation of the product is product of expectation, but that guy has expectation 0, so it just drops out. And so that means the expectation shouldn't change. Okay. This expression here, well, one can just compute it, and the expectation of the exponential of a Brownian motion does actually change over time, and it's precisely e to the t over 2. And so if I multiply it by e to the minus t over 2, then I do get something which has an expectation that doesn't change over time. Okay, so that tells me that this is in some sense more likely to be the correct. This is certainly no way that this can be the correct answer just because of that argument, even though we almost had a proof of it. And this has a better chance of being the correct answer, but at this stage, we really don't have a proof of that. Right? So how comes that this formal derivation gave us the wrong answer here? So the reason here, which it almost looked like a one-line proof, right? So it can't be too hard to actually figure out where in the line it goes wrong. And the point where it goes wrong is that, of course, we sort of try to take a continuum limit, but the W, this Wiener process in the limit, we've seen it actually really doesn't look like a differentiable function. Right? So dw by dt really doesn't actually exist as a function. Now, if you're an analyst, you'd say, well, okay, so that's not a problem. I know how to differentiate anything because I just interpret it as a distribution, and then I can always differentiate anything I want, right? But then the problem is that distributions are really nice, but you're not allowed to multiply them, right? So that's one of the problems with distributions. You can multiply them by smooth functions, but here what we would like to do is multiply that dw dt by S itself, and S itself is not expected to be any more regular than W because we expect it to be something like that. And so this is actually only a Hilda, not quite a half type function, right? So it's a very irregular kind of continuous function. And in general, if you have an arbitrary distribution, you can't multiply it by a kind of irregular function. So actually there's a refinement, right? So there's the theorem which says, okay, so you can always multiply distribution by a smooth function. You can improve on that theorem by saying, well, if the distribution is not too bad, then I can multiply it by functions that are a bit worse than just smooth, right? And then at some point, these two kind of, hit each other. And so the theorem says something like that. So if you have a function and a distribution, the product is sort of well-defined. If the function is alpha Hilda and the distribution is sort of beta Hilda in quotation mark, where beta might be negative, as long as alpha plus beta is positive. Okay? And so here, the regularity of my function, I expect it to be basically a half, but just below a half. And then the distribution is the derivative of something which has regularity just below a half, and well, taking derivatives drops the regularity by 1, so that's just below minus a half. Right? So here I'm in the situation where this is just below a half, this is just below minus a half, and a half minus a half is 0. And if I'm just below, then I'm just below 0. And the theorem says it's well posed if and only if you're just above 0. Okay, so I'm just out of the scope of that theorem. Right? So I'm almost in the scope of that theorem, but I just missed it by a tiny amount. And the consequence of basically being at the borderline of that theorem is, well, exactly the thing that we've seen, right? So it's that actually the product between these two is essentially ill-defined. But the interesting fact is that it's not totally ill-defined. Okay, so it's ill-defined but as long as you take reasonable, and you can make precise what you actually mean by reasonable, but as long as you take reasonable approximation of that ODE that I wrote down, you're going to get a limit, and the limit is always going to be of this form. It's just that you're going to end up with different values for that constant C, depending on how you take limits or how you approximate it. And so here there's sort of the moral of this story. So this story seems at this stage almost sort of unrelated to the previous story. The only relation at this point is that, well, there's something which sort of appears ill-defined. You fiddle around, you can still give it a meaning, but then what you naturally end up with is sort of like a one parameter or several parameter family. And what's well-defined is the family. but the parametrization of the family is not necessarily well defined, right? It doesn't come with a canonical parametrization. Okay, and that's exactly what we see here, is that we have this family, but you know, which one is the right value of C depends on how you approximate that ODE, right? So if you just write ds dt equal to s dw dt, and I don't give you any other information, basically what you can say is that, well, S here should be one of these functions, but I can't really tell you what the value of C is because you haven't given me enough information to tell me how this product here should be interpreted. In this particular case, there's this whole Ito-Stratonovich business that maybe some of you know very well, which tells you that in a way there are two natural values of C, which is sort of, well, 0.5, which are the two values that we've seen actually on the previous slides, and they are in some sense more canonical than the others. But still, depending on situation, one of them is more natural, and depending on situation, the other one, right? So, and so now I want to change gears and show you some more recent stuff, right? So this is actually all, in some sense, you know, mathematics from the 60s. So I want to show you also some recent mathematics, and so the example I want to show you is sort of the analysis of interface growth models. So here the situation is you want to find a sort of universal model of interface growth in a similar way as, you know, Brownian motion is sort of a universal model for, you know, fluctuations. And so in this case, so an interface growth, so the sort of interface that we're talking about is, imagine you have a two-dimensional region, and the region is separated in two. Okay, so, well, since, well, you've got wildfires going on, so the, you know, the two-dimensional region would be the bush, and there's one half of it which is burned, the other half which is not burned, and there's a flame front between the two. Okay, and the flame front is the interface between the burnt and the non-burned part. And now that flame front is going to move in one direction, right? It's never going to retreat back into the burnt bit. It's always going to invade the non-burned bit. And it's also, even if it starts out straight, it's not going to remain straight, right? Because there are bits that are going to burn a bit faster, bits are going to burn a bit slower. So even if you start up straight, it's going to roughly move in a straight line, but then the line kind of starts to fluctuate, okay? And what you're interested in here is some kind of universal model for these fluctuations. And so here are actually experiments. So this experiment is the lab version of a flame front, which is you take a very thin sheet of paper and you sort of put it on fire on one end, you sort of zap electric current, you make it very flat, you put an electric wire on one end, you zap a current through it, so then it starts burning, and you kind of record it every couple seconds or so. And this one is a much more precise experiment where you actually do something with liquid crystals. So there's a liquid crystal that comes in two phases, and you sort of prepare it in the unstable one. And then you zap a laser beam on it that sort of flips it into the stable phase, and then the stable one invades the unstable one. And you look at the interface between the two. And in that liquid crystal, you can just literally see the interface because it has the two phases have different optical properties. So you just take pictures with a high resolution camera, and then you sort of superimpose these pictures. And so you get a kind of picture of this front that moves, and you see these fluctuations here at the top. Okay, so now you can come up with lots of mathematical models. So these are 3 simulations for 3 different kind of models that are supposed to model a situation like that. Okay, so let me show you. So here is this is an example of one of these models. Oops, actually, this is the example. So here you see these bricks, if you want. And the way they grow is you imagine that you have sort of bricks falling from the sky, and they just pile up, but they also stick to their neighbors, right? So that's why you can see these overhangs. Okay. So you have these overhangs forming here. And now what you're interested in is the fluctuations of this at very large scales. So you kind of zoom out and you see something like this. So let me pause that. So here you see now if you do it at large scale, so here it's maybe, I don't know, 4,000 bricks wide. And I've done, well, 17 million bricks here. And you see the interface at the top, which, is random and sort of fluctuates in a way. Now this gives you, well, the hope is that you would actually get a limit, which is non-trivial if you scale things correctly. So here you would actually have to zoom a bit out vertically, right? Because it kind of gets quite flat. So you zoom out vertically in the correct way. The hope is you get a random limit, but now it's not just a random continuous function of time, it's a random continuous function of space and of time, right? So it's kind of a random movie that you get in the limit, and you want to describe that random movie. So you have lots of different mathematical models that have same features, and the conjecture here is that they all have the same scaling limit. You zoom out, you scale things correctly, you recenter it so that you look at what happens at the top of the interface. You should get the same random continuous function of space-time for all of these models. And that's something that one doesn't, it's really conjectural. So there's been lots of progress recently. So there's about 3 years ago, Matetsky, Quastel, and Bremenick came actually up with a complete characterization of that limit that you get, this random continuous function of space-time. And they got that by showing that one specific model has a limit. Okay, so they showed for one specific model that there's a limit, and they can actually characterize the limit. It's a sort of very complicated characterization, but it's a full characterization. And more recently, there's actually 2 independent works, one again by Quastel and a collaborator, and one by Balint Virag, who interestingly is in the same department as Jeremy, so they're both at University of Toronto, but they have these 2 proofs of the same result that were obtained completely independently by 2 office neighbors with 2 completely different techniques, which is a kind of interesting story. Anyway, so they have these recent results where they show that a larger class of models actually converges to the same limit. And the nice thing is that the 2 techniques kind of generalize the original result in very different directions. So the intersection of their results is non-trivial and new, but then it generalizes in different directions. Okay, so there's sort of lots of recent development here, but still we're very far from having sort of a proof that at least gives you, something where you feel, oh yeah, so this really explains that most of these models should have the same limit, right? So right now the proofs are somewhat ad hoc, and they work for very specific classes of models, right? So it's not like Brownian motion where one has very general theorems that tell you that, pretty much anything you can think of converges to a Brownian motion if you look at it in the right way, right? So we are not at all at this stage here. And so one thing that one can try to see is one can try to prove also these universality results for something what I would call a crossover regime. So here what happens is these interface growth models that I mentioned to you, they were directed, right? So like the fire is clearly directed. It moves forward, it never goes back. The simulation I showed you is also directed. So you have bricks falling up, they pile up, but they never go back. So you can also have situations where you have an interface between 2 regions where the interface can move in both directions. And you can have situations where the 2 regions are completely symmetric. So the interface fluctuates, but it fluctuates in the same way, sort of back and forth. One example is in statistical mechanics, for example, the easing model. If you look at if you're at 0 magnetic field and you have sort of a region of pluses, region of minuses, you look at the interface between the 2. It has fluctuations. It doesn't make any difference whether you put plus on the left, minus on the right, or vice versa. The fluctuations are completely symmetric. Okay, so in those situations, one has a much better understanding of these fluctuations, and they're expected to be Gaussian, and one has some kind of central limit theorem. Okay, so there's still a space-time object, but they can be described actually as solutions to the stochastic heat equation, which is this equation here. So you delete these two terms. It's just here the heat equation, and here you have a term which is called space-time white noise. So you should think of that as being a random function of space and time, which is such that the correlations are delta functions in space and delta functions in time. So it's sort of like independent noises at every point in space and time. And so while the solution to this is linear inhomogeneous, so the solution is some linear function, linear map applied to that guy. This is Gaussian. You apply something linear to it, you get again something Gaussian. You can just write down what the correlation functions are. So you have a complete characterization of that. And so now you can ask yourself, what if I'm in a situation which is almost symmetric, but not quite? Right? So for example, in the Ising model, put a small magnetic field. Right? So then one region is favored, and the interface would want to start to move. So it can still backtrack, but on average, it moves in one direction. And then one would expect this to actually have the same limit as all the previous models. And so this limit is called the KPZ fixed point, by the way. So one would expect that to converge to the KPZ fixed point at large scales. But now I can ask myself, what if I do a sort of joint limit? So if I can tune the asymmetry of my model to make it almost symmetric, and so I tune the asymmetry to 0, and at the same time I zoom out, and I zoom out just sufficiently far that I start to see a deviation from this linear model. Right? And then you can ask yourself, what's the deviation that I see? And you can do a kind of formal calculation, and the formal calculation tells you that what you should see is this equation here. And so that formal calculation was done by, well, KPZ, so that's Kaldar, Parisi, and Zhang. That was back in the mid-80s. Okay, so you just sort of write down this equation. But then if you look at this equation, you'll see, well, actually the equation doesn't really mean anything. So here the problem is much worse than the one with that we saw earlier in our sort of asset price model. The problem here is that you have this term which involves the square of the derivative of the solution. But actually, if you look at this linear equation, so the one without this stochastic heat equation, solutions to this equation at any fixed point in time, as a function of x, they actually look like a Brownian motion. So as a function of x, they look like one of these functions, which is, you know, Holder not quite a half. So now, you know, here the h is Holder not quite a half, so the derivative is a genuine distribution at every point. And now you're squaring that, right? So now there's no way that this can end well, right? Because you're squaring the derivative of something which doesn't have a derivative. And so clearly that, you know, if you take any sort of approximation to this, this guy is going to blow up. It's just going to go to infinity. And so what you would want to do is, well, you know, the natural thing to do is you somehow regularize this in some way. And now what you do is you just, this constant here, you can actually view it just as a change of reference frame. Right? So adding a constant here is actually the same as just looking at the solution in a reference frame that moves up with the solution itself. Okay. So here on the right-hand side, you have this term which is very positive. That means that h is going to grow very fast. And now you just put yourself in a reference frame when you move up with it at constant speed. And you call that constant speed C epsilon. And so now here the theorem is that, well, you can choose, if you choose that constant correctly, then whichever way you regularize your white noise, right? So here you regularize it basically by somehow replacing these delta functions by some approximate delta functions, right? And so now there's lots of different ways of approximating a delta function. The claim is you always get the same limit, right? So you can choose, the constant C epsilon would depend on how you regularize things, but the limit you get is always the same, or at least it's a one parameter family limit, again, as before, because in some sense, there's no natural reference speed, right? So you could kind of change the speed of your frame a little bit by a sort of order 1 amount, and you would again get a possible limit, which you get by just changing the constant by order 1. So you get a 1-parameter family of limits, but they all differ in a trivial way from each other just by a change of reference frame. Okay. And actually this result turns out is very stable. So this result is very stable in the sense that, you can, for example, take a larger class of models. So here I can take this class of models here, so this is actually more like goes in the direction of how the equation was derived, in the sense that the noise here is order 1. So you take any smooth noise, actually it doesn't even need to be Gaussian, some sort of stationary random field. It needs to have good enough kind of mixing properties. And then here you take any polynomial, or actually now it has even been generalized, right? So you take a smooth even function. So you put a nonlinearity here, which is just some function of the derivative, smooth and even. And you put a small parameter here, right? So this is the asymmetry of your model. So if this was 0, then this model is symmetric under h goes to minus h, at least assuming that the fluctuations here are symmetric under sign change. Okay, so now here you have this small parameter that we use to tune the asymmetry. And then the theorem here is that, well, same as before. So you can kind of just rescale this solution, right? So you look at spatial scales of order 1 over epsilon, and then it turns out that the correct way is to look at time scales of order 1 over epsilon square and rescale it vertically by square root of epsilon. And if you scale these things correctly, and you subtract the correct constant times t, that's sort of the average speed of the thing, then you actually get you converge to a limit, and the limit is the solution to KPZ. And the interesting, so this lambda here is just the lambda sort of in front of the nonlinearity. If you do a formal calculation, if you just write P as, some constant times dxh square plus another constant times dxh to the 4 plus and so on, right? Then formally, if you do that change of scale, what you see is that the quadratic term stays as it is. Well, or somehow the square root epsilon gets dropped, so the quadratic term comes up with an order 1 constant, and all the higher ones sort of drop. They come up with powers of epsilon. So naively, you would think that in the limit, that lambda is actually just, the quadratic term of P sort of at the origin. But that's not true. Okay, so the lambda here is actually some kind of average of so it's not the second derivative of P at the origin, but it's actually an average of the second derivative of P with respect to some Gaussian measure. So it's not completely trivial if you want to actually even guess the value of lambda here. But this theorem is pretty general, right? So this can be pretty much any function, this can be pretty much any field. So you have a very large class of models for which you show that you can actually converge always to the same limit. So let me, right, so I have 1 minute. So let me just spend 1 minute to give you a very quick idea of how do you prove results like that. And then I'm going to sort of explain a bit more in details the, sort of technical aspects of that in the 2 lectures that I'm going to give in 2 weeks' time. Right? So the problem here is that, right, so you have something that looks a little bit like some kind of approximation of some limiting equation, but the limiting equation doesn't have an obvious meaning, right? And the reason why it doesn't have an obvious meaning is that solutions aren't smooth, and you want to perform operations on the solutions that are not well defined on smooth functions, like taking the square of the derivative. And so here, so first, what does it actually mean for something to be smooth, right? Being smooth really means being well approximated by a polynomial, right? And the degree of smoothness is just, the degree to which you are well approximated by a polynomial locally. And so now the idea is that you could change the way you measure smoothness, right? So you could, so in this case, we're looking at this weakly asymmetric situation. So you could say, well, locally my solutions should be reasonably well approximated, for example, by the symmetric guy, the solution to a symmetric equation. But then there are maybe higher order terms that you can guess. And so you can try to use these as analogs of the polynomials and say, well, instead of measuring smoothness in terms of how close I am to polynomials, I measure smoothness in terms of how close I am locally to some linear combination of these random, very rough kind of functions. But it turns out that you can build a family of such functions in a natural way, depending on the problem you're considering, in a way that they also have algebraic properties that are, and analytic properties that are actually very similar to those of polynomials. And so they make good replacements, if you want, for local Taylor expansions. And then you can say, well, you know, how do I perform an operation like multiplying two things? Well, actually, what I need to be able to do is I need to be basically able to multiply their Taylor expansion. So if I can multiply their Taylor expansions locally up to sufficiently high order, you know, then it's sort of reasonable to expect that I can actually really out-multiply these two functions. And the right order really means sort of up to order 0, right? And that's the 0 that appeared in the previous theorem about function times distribution, where we said the sum of the regularities has to be positive for the product to be well defined, right? That in some sense tells you that, you know, the function has a Taylor expansion, the distribution doesn't. And so in some sense, the distribution has negative regularity. So in some sense, it has a Taylor expansion of order of that negative regularity. That's the way you can kind of think of it. And the function has some positive order Taylor expansion. You multiply them. You want the order of what you get to still be positive. And if that's the case, then the product is well defined. Okay, and this is a completely general theorem, right? So you can prove a theorem like that, which holds for pretty much, you know, any way of defining Taylor expansion, as long as you're actually able to multiply the terms in your Taylor expansion. Okay? And so then all you have to do, in some sense, the problem of defining these products becomes a problem of defining products between sort of a finite number of somewhat explicit terms. And the fact is that actually if you do that, then for the solutions to these equations, even though in the usual way of measuring regularity, they are very irregular, in this way of measuring regularity, they're actually smooth. They actually see infinity in a way, right? So you can prove that they have regularity of arbitrary order. And yeah, so I think, so here I have a sort of more general picture, but I think I'm out of time, so I should stop here, and thank you very much for your attention.
Thank you very much, Martin, for a very enlightening talk. Are there any questions?
Oh, I think there's a question in the chat.
There is a question for Jeff
Let me see. For something like KPZ, the shift constant depends on type of regularization. It might sound like bad news comparing to things like boundary motion, but it's actually not. Constant gives information. Right. Yes. So then the question is, how much information does the math give about the functional form of these constant terms of a particular way? Yes, it does actually give you. So for example, I mean, these constants have sort of very explicit expressions, right? In particular, you know how, right, so this constant C epsilon, if you want to sort of know how it depends on P, typically what happens is that it has some sort of expansion in powers of epsilon and maybe logs. And in this particular case, it's actually, it only has a 1 over epsilon term. There's a log term, but the log term actually cancels out. So in some sense, there is a sum of terms that do diverge logarithmically, but they always cancel out for every choice of regularization here and for every polynomial. And you can, you can see somehow for these terms, you can kind of figure out how they depend on the various other parameters in the equation, right? So if you want, the functional form of these constants is sort of, very explicit. Is this something specific to 1D? No, it's not specific to 1D. and actually, even in this example, it's not quite right. So it's 1 plus 1D, right? So it's space-time. And these expansions here, you have to actually do them in space-time, even for that KPZ. Well, no, you don't. Okay, so in KPZ, you can just about get away with doing them only in space. But you can do, there are other equations you can treat with the same sort of methodology that are in higher space dimensions.
I've got a question. In your remark on the previous slide you showed, at the bottom, yeah, KBZ, you do have Gaussian noise there, right?
No, but that has been dropped already, actually. Yeah, so yeah, you don't need to assume that this is Gaussian. So by now we can do it with quite general noise. So there are somehow conditions on the cumulants of the noise, but it doesn't need to be Gaussian.
Okay, thanks. I was wondering whether there was a noise model, maybe extreme noise model, for which you
right. Okay. Yeah. So you need right. So you need high order moments. Okay. So you certainly need high order moments. So if you start to put in noise with heavy tails, then you might get something different.
Okay. Thanks.
I have a question. Regarding the limits, you showed us example, or you reminded us that for stochastic differential equations, you can have more than one limit depending on the choice of approximations.
Mm-hmm.
In limits which you discuss for stochastic PDEs, like for KPZ equation, are there any examples when you can have more than one limit depending on type of approximations?
Yeah, so here you always, right, so even here, it's sort of like you have a family of limits, and the family of limits are sort of, parameterized by that constant C, right? Because you see, the theorem tells you that, so in this particular case, the theorem tells you that if you choose, there's a way of choosing C so that this converges to a limit. But if I replace C by C plus 1, then it's still going to converge to a limit, right? So I have a one parameter family of limits. And so in this particular case, there is one which is more natural, which is called the Kohl-Hopf solution, because you can somehow turn this into a heat equation by looking at the exponential. And then that one, you can define its solution in Ito sense. And then you just define H as being the log of those solutions. And that fixes, if you want, that constant, but that relies again on, defining solutions of the other equation in the Ito sense, which already in that sense is also, there's a indeterminacy there. There are other examples. So there's a large class of examples. So if you want the largest class in one dimension that you can treat, yes, and that goes with that actually kind of answers the question that's in the chat right now. So I suppose that's good. So you can actually look at components, and so you can actually look at a whole class of things like that, right? So if I take, well, let me call it U, say. So you can put an arbitrary function here of U times dxu beta, dxu gamma. Well, then you say sigma I of U alpha psi I. So you could look at a class like this. Of course, here I can also add things that are kind of linear in dxu and things that are just functions of U. And so this class of equation, it shows up naturally because if you look at, for example, like a nonlinear, if you think of a one-dimensional, so that has then nothing to do with interface growth, but if you think of a one-dimensional SPD that takes values in a manifold, and then the natural heat equation with values in a manifold is exactly of this form, where the gammas would be the Christoffel symbols of the manifold, and that's why I wrote them as gammas. and these guys generate the metric. And so if you apply so you can apply the whole theory to that. And there, if you want, a priori, the theory gives you 54 or 56 or something different renormalization constants. So you end up not with a 1 parameter family, but with like a 56 parameter family or something. And then you have to ask yourself, you know, can I impose additional properties in order to reduce that? So can I make things more canonical in order to impose additional nice properties on my solution theory? And so like for SDEs, well, you know, Ito solutions satisfy Ito isometry, Stratonovich solutions satisfy change of variables formulas. So you can impose, you can actually have analogs of both properties here. And here it turns out you can actually impose both at the same time. So you have solutions that are simultaneously Ito and Stratonovich in some sense. And that reduces the number of parameters from like 54 to 2. And in the natural geometric case, one of the two also drops out, and then you're down to 1. And that one, there's actually a natural way of fixing it as well. So here, there's actually a way of going from like 56 parameters to essentially 0 parameters in the natural situation. And if you do that for KPZ, you do end up with the Kohlhoff solution. Okay, so that's.
Any other questions? If not, let us thank again the speaker and all participants who asked questions, and we will meet tomorrow again at 8 p.m. Sydney time. Thank you very much.